Now we want to talk about how gravity really interacts with other objects. Now, this is all coming from Sir Isaac Newton. Okay, Sir Isaac Newton, the story goes that he was sitting under an apple tree. He gets hit in the head with an apple and goes, "Hey, that's gravity," which really probably did not happen. But what did happen was this. He talked about how the gravity of the moon being attracted to Earth was the same type of force and the same thing going on with just an apple falling towards us on Earth. And so it was the big tie-in to put those two together. So that's what we're going to talk about today. Hey everybody, it's Mr. Spudik again. Today we're going to talk about Sir Isaac Newton's universal gravitation. Okay, and the idea is understanding more about gravity. Sir Isaac Newton is going to, him along with the work of Kepler, really build our solar system. And he wanted to look at gravity in terms more about the numbers and about how things are working compared to planets and everything else around us. And if you think about Galileo did a ton for us. Galileo was the one that really broke down to help us understand gravity and how much things speed up. And Sir Isaac Newton wanted to understand more about the forces involved and understand the forces and how two objects interact. So what we have here is Sir Isaac Newton's equation, which is the force of gravity is equal to a constant, a value that we're going to just give the capital G, capital letter G, which is not my rap name. My rap name's little g, okay? But we have capital G there. We have two objects, and they have two masses. And then we have our radius. And even though we say radius, it's the distance between two objects. Okay, now, what Isaac Newton's saying is for any object that has mass, any object whatsoever, there will be a force of attraction with it and any other object that has mass. Okay, now obviously the objects that are really going to show this mass off are huge objects. Okay, when we're talking about planets, at least one of these masses should probably be a planet for us to notice it. But let's break down and look at this equation a little bit more. Okay, what is this little or this capital G? This capital G is a constant that we will always know, and it's 6.67 times 10 to the negative 11th. So you will always use that number, always in your equation. You will always be given that number, 6.67 times 10 to the negative 11th. So anytime you do the calculation, you can start with that value, 6.67 times 10 to the negative 11th. Okay, we have m1, which would be the mass of any object, times m2, the mass of any other object, and r squared, again, is just the distance between the two objects. Okay, specifically, we should probably say the center of gravity. Okay, if you've learned center of gravity already. So if we were talking about two planets, it wouldn't be, you know, the surface of them, but the centers of gravity between those two objects. But for any object, okay, so the Earth and the moon, there was obviously gravity that's keeping the moon in orbit around the Earth. Okay? The sun and the Earth, same thing. A different force, but you could take the planet, you could take the sun's mass, okay, make it m1. You could take the Earth's mass, make it m2. Get the distance apart, separating the two objects, okay, and you could figure out the force of attraction, the force of gravity between those two objects. But why do they say universal? I mean, really, it's because any two objects, okay? Any two objects have gravity. So why is it if I walk by a building's pretty heavy, right? It's not like I fly and slam into the wall of a building. The mass has to be so huge that it's on the level of a planet for you to feel that gravity, okay? But there really would be some type of gravity pulling me towards the building. It's just so small we never notice it, okay? Why is it so small? Well, think about this value here, G. 6.67 times 10 to the negative 11. All right, think about what type of value that is, though. Any number you multiply by 6.67 times 10 to the negative 11 is going to be a really, really small number. Okay? So if we have, let me just, and if we wrote this out, if I had 6.67, and I want to do times 10 to the negative 11, that would be 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. There's my decimal. That's pretty small, right? And so this is where you hear scientists talk about this weak force of gravity. I don't think anyone that's fallen down thinks that gravity's pretty weak. But if you compare it to other forces out there, it really is. Okay? And it's all because of this value here, this G, makes everything so much smaller. Okay? So all the planets, those forces you can notice. But any object, from what Einstein, or from what Sir Isaac Newton says, not Einstein, that goes a different direction. Okay? Whatever Sir Isaac Newton says, there's a force of any two objects that have mass. Okay, let's give this a shot. Okay, let's say that I have two sumo wrestlers and they're both 150 kilograms. All right, so how would I figure out it? And I also have the radius. Okay, they're both 1.5 meters apart. Why don't you try and calculate what that force of attraction will be? How do we do? Okay, let's go over and see. So how are we going to use this universal gravitation formula? So we're looking for the force of attraction between those two objects. It will be equal to G times M1, M2 over R squared. If we plug in our values, we have 6.67 times 10 to the negative 11th. Now, I want you to practice and look at your calculator. If you have a Casio or you have a TI, you should see a button that's usually two capital E's or maybe an EXP button, and it's going to change this times 10 to the into a capital E. Okay, but I'll show that later. So I have 6.67 times 10 to the negative 11th times 150 times another 150 divided by 1.5 squared. Okay, so if we multiply those out, we will get a value of 6.67 times 10 to the negative 7th. Okay, I probably should have picked better numbers. Sorry. But think about that force. We have two sumo wrestlers. Okay? We have two sumo wrestlers, and if we're going to have 6.67 times 10 to the negative 7th, that's 1, 2, 3, 4, 5, 6, 7. Okay? And that's in newtons. Okay? Think about your force of gravity is going to be in the hundreds. Right now, you are feeling gravity. You're feeling a force of hundreds of newtons pulling you down. Okay? Sumos would never feel that kind of force of whatever they're standing between each other. Okay? All right. Let's think about that compared to your weight, like I just started to do. If your mass was 75 kilograms, all right, we've learned about this before. I just want you to remember what your weight, right? Weight, we had force of weight was equal to mass times gravity. So 75 kilograms times 9.8, you get a weight of 735 newtons. Okay? So understand this. That force of 735 newtons is also coming from Sir Isaac Newton's universal gravitation. Okay? So this force is what you would get is if you had big G, 6.67 times 10 to the negative 11th, times the mass of the Earth, times your mass, okay, so we'll put a little E there for Earth, okay, your mass, which you already know is 75 kilograms, divided by the distance between you and the center of the Earth. Okay? All right, so everything we've learned already about weight from before ties into universal gravitation. Okay. I just want to point out something with orbit. A lot of people will think about astronauts, okay, or people in the International Space Station, and they say, oh yeah, there's zero gravity there. That's not the case, okay? When astronauts are orbiting around the Earth, they still have quite a bit of gravity, okay? It's just that they're in constant free fall. And I won't go into all of that explanation right now. But understand that when people think there's no gravity, there really is a lot of gravity. There really is still gravity. If we just looked at that formula for universal gravitation and we saw that it's F, G, M1, M2 over R squared, okay? Radius is important. And the satellite did move further away, okay? Or people in the space station are further away than you and I are standing on the Earth. But that's not a big difference, okay? You're talking about a value of times 10 to the 6, and we feel, and our radius is about 6.35 times 10 to the 6, and they're only 6.65. That's not a huge change. So there's still plenty of gravity, okay? They might not be feeling exactly 9.8, but they are definitely feeling a good amount of gravity on the space station. It's just that they're in constant free fall, okay? The value down below is just something I grabbed off the web, but it talks about how fast they have to go to be in orbit. And we're looking at roughly 7,725 meters per second for a satellite. That's how fast they go horizontally, okay? Or miles per hour, 17,285 miles per hour. All right. With universal gravitation, this formula is not too tricky. You're going to do your algebra, solve for one thing, solve for the other. You could solve for a mass. You could solve for the radius. Any of these things, you could do some algebra to do it. But physics teachers love to ask questions more, with this formula especially, of if I increase this, what's going to happen? If I double one mass, what's going to happen to the new force? How much bigger is that going to be? Okay? If I double or triple a mass. But the big one that we always want to talk about is the radius. Okay? If you double the radius, if you triple the radius, what happens to the new force? Okay? It's so important in physics that we have a term for it. Okay? We call it the inverse square law. And the reason we call it the inverse square law, let's think about it. When we're talking about this radius, for one, we see that the radius is on bottom. So if you think mathematically, if the radius gets bigger, okay, and it's on bottom, your force should get smaller. Okay? So first off, we see the radius is on bottom. Okay? It's inversely related to the force. So we know that if the radius goes up, the force is going to go down. Okay? But by how much? All right? We also see that it's squared. So if I double something that's squared, I get something that's 4 times bigger. Okay? And the same rule applies here. So if I doubled the radius, so let's say, and so let's use the idea of, let's make every other number on this equation 1. So let's pretend that G is 1, which it isn't. But let's just make that value 1. Let's make mass 1, 1. Let's make mass 2, 1. And let's just make the distance between two objects only 1 meter for the first time around. So 1 times 1 times 1. If we first try it out, we have 1 divided by 1 squared. Okay? So if everything is 1, I'm going to get an answer of just 1. Okay? 1 over 1, just 1. What happens if I double my distance apart but keep everything else the same? Okay, capital G is still 1, mass 1, that's still 1, everything's 1. So 1 times 1 times 1. But now I double my radius. So I have 2, and I'm going to square it. Okay, on bottom now, I have a 1 divided by a 4. So, if I double my radius, my new force will be 1/4 of my original force. Okay, that's the explanation of the inverse square law. It's on bottom, so it's inverse, and the radius, the r in the equation, is squared. What about if we triple? Okay, if I triple my radius, how many times smaller will my new radius be? I'm going to freeze it here and let you answer. Are we ready? Okay. All right. If I triple my radius, well, now I have still a 1 on top, because everything on top is still a 1. Okay? But now I have a 3 down below. So now my new force will be 1/9 my original force. Okay? So radius is extremely important, and when you change that radius, it changes the force much more than anything else in that equation. Okay? And that's what we call the inverse square law. You should expect from your teacher that you will have a lot of practice. If I double this, what's going to happen? If I triple that, what's going to happen? Not just radius, but also mass. Okay? And it's just going to be plugging in numbers. But it's so important. That's why we keep practicing and give this the inverse square law name. Okay. My last thing I just want to say is gravity. We know a lot about gravity, right? Gravity is pretty well known. We got Galileo helped us a lot. Sir Isaac Newton just gave us this. They were able to build the whole solar system with it. But really what's interesting is we still don't know that much about what gravity really is, how we get gravity. Okay? And for all this stuff that Sir Isaac Newton can use and build the solar system, as we move along to other things, okay, and we talk about Einstein, Einstein's going to really blow the doors off everything Sir Isaac Newton has done. Okay, but that's for another lecture. Thanks so much for watching, and I'll see you again later.